Okay, I'm going to try to get you out of here early tonight because you probably haven't had dinner. So we have just one speaker tonight after me, and boy, do we have a speaker. Kevin Trenberth was a scientist at NOAA. No. NCAR, National Center for Atmospheric Research.
Ted?
Yes, sir.
If you speak into the microphone really loud, then it'll come out on the video.
I'm sorry. Okay, how's that? I'm kind of lazy about that. Kevin Trenberth was the principal author of the IPCC report, the International Panel on Climate Change, that raised a lot of eyebrows predicting global warming. Would you believe it? Well, this year, the temperatures in Denver are about 5 degrees higher than they were 4 years ago. You can believe it or not. We've had our fires, we've had the drought, we've had the floods. Now, the title of Kevin's presentation 4 years ago was Global Warming, Coming, Ready or Not? And, of course, there was some discussion, there was some disagreement. Well, he's going to continue respond to that. Anyway, Dr. Trenberth received a Nobel Prize, shared a Nobel Prize with the panel, Nobel Peace Prize for that report, which has become kind of the holy script of those of us that believe in global warming. And he's our high priest, I would say, if you don't mind saying so. So please welcome Nobel Prize laureate Dr. Kevin Trenberth. Okay.
Good evening, everyone. Welcome to Colorado. How many of you are from the West? So you will know that it's been drought, and a lot of wildfires.
We can't hear you very well back here.
You can't?
Let me try boosting it until it's...
Well, I don't know. How's that? Don't want to too late.
More.
It'll be feedback if we turn it up anymore.
Well, what about using the microphone like you did? That works.
He has a microphone.
Yeah, but I mean the microphone hole. That would work better. It would.
I'll move it right up. All right. So I'm going to talk today about a little bit about background of global warming. Some of you may have heard me a few years ago, but I want to talk a little bit more about extremes of climate change that go along with global warming, because those are the things that have a really big impact, and they're really expensive. And we are experiencing a lot of these now in ways that really matter. And so what I want to try to do in this talk is to give you some explanation as to why these occur. And we'll see how it goes. That didn't do anything. We'll try this. It's not doing anything either. All right, try this. Here we go. So this is a summary of the overall problem. If the planet were to go to see a doctor, for instance, then the symptoms are that the planet's temperature is suddenly rising. Carbon dioxide in the atmosphere is also increasing. So those are basic observational things. The diagnosis is that these two things are related to one another. We think we can prove that. And that the human activities are causal because they cause the increase in carbon dioxide. The prognosis then is for more warming at rates which can be disruptive. The rates of change are an important factor in this and will cause strife. The treatment, these are key words in the language, in the vernacular that's used in the whole climate change arena. Mitigation, which really refers to, in this case, reducing emissions of carbon dioxide into the atmosphere and other greenhouse gases. And adaptation refers to planning for the consequences, coping with whatever is going to be put before us much better than we are right now. No, that's not working. All right. So, whoops, we went one. So there we are. What's causing the warming? And basically we are, right? And the evidence for this comes very much from pictures like this, which show you over time the amount of the sources of our energy supply, and it's basically an exponential kind of curve that highlights a tremendous increase, especially after about 1960 or thereabouts. And most of this is from fossil fuels. So there's a little bit down the bottom here, nuclear and other sources down the bottom, hydro and so on. One of the consequences of this is increases in carbon dioxide. Since 1958, Dave Keeling started measuring carbon dioxide at Mauna Loa on the top of the hill, on the top of the Mauna Loa mountain, away from any influences of the city. And it shows the sawtooth character, which is the drawdown in carbon dioxide as the planet breathes in and breathes out with the seasons. So as the greening occurs in the springtime, there's a drawdown of carbon dioxide, and as the decay of leaves on the forest floor and so on occurs in the spring, in the fall, then carbon dioxide goes back up. So this is the natural annual cycle. And superposed on that, you can see this overall upward trend. And you'll notice also that this upward trend is increasing. And so we can look at arrows at various points on this curve, and we can see that the rate is actually increasing, in spite of efforts like the Kyoto Protocol, which are supposed to turn this down in the other direction. And of course, the reason for that relates to all of the industrialization and the developments that are occurring, especially in China, also in India, and some other parts of the world in particular, but the U.S. contributes a substantial component to that as well. So I'm not going to go into that aspect of it here. I can answer questions about that aspect. One of the consequences then is that we're changing the composition of the atmosphere, and the greenhouse effect plays a key role. So the sun is beating down. The sun's rays mostly come through the atmosphere, which is relatively transparent to the sun's rays, unless there are clouds which reflect the radiation, or at the surface. And the total amount reflected is about 30%. So to keep an overall balance, everything radiates, but some of that radiation is trapped by the atmosphere. It's absorbed by certain gases, the greenhouse gases in the atmosphere, and then re-radiated up and down. And because it's cooler, higher up, then it radiates to space with cooler temperatures than it otherwise would, and it actually makes our planet habitable. So this is the overall greenhouse effect. And then if we change the composition of the atmosphere, we trap more of the radiation. We interfere with this natural flow of energy through the climate system, and it has consequences. It's the global warming aspects of this problem. So we can compare a number of things here with the incoming energy from the sun. The incoming energy from the sun amounts to, on an annual average basis, on a global average basis also, 175 billion watts, 175 petawatts. That's 175 with 15 zeros after it, 15 zeros. About 122 of those is absorbed. And so that's what drives all of our water cycle, all the hydrological cycle, all of the weather. The other 30% is what is reflected back to space. Now, the biggest power plants in existence are about 1,000 megawatts. There's some up to around, 1,600 megawatts or thereabouts. And, on a day-to-day basis, we normally think of things like a 1-bar heater, 1 kilowatt, an iron. Kids these days don't use irons, so they probably don't know what that is. It's about a kilowatt or so. And, 100-watt light bulbs. Actually, we don't use light bulbs anymore either. We have these spirally things instead. But, those are sort of the familiar terms that we use. And the energy from the sun is 122 million of these power stations. And if you add up all of the power stations all around the world and all of the other energy from burning of wood, anything else that we do, the best estimate is that it's about 1/9,000th of this amount of the natural flow of energy through the climate system. And so by that measure, it's relatively small. Now, in some places, it is very concentrated in cities, and that gives rise to a different climate in the cities. It's called the urban heat island effect, and it relates to having a concrete jungle, less water lying around, and different reflectivity and all the space heating that goes on in cities, or air conditioning and things like that. And so in cities, those numbers can be quite a bit larger, but still, on the whole, not contributing to an overall influence on the climate, except very locally. So the main way human activities affect the climate is not by competing with the sun directly, but rather by interfering with these natural flow of energy through the climate system. So the IPCC findings, this is the 2007 report, indicates that there's a whole lot of symptoms relating to warming. There's decreases on stuff on the cold side. There's rising temperatures in the ocean, in the atmosphere, at the surface, melting of ice. Global sea level is rising. And then there are changes in aspects relating to water and the water cycle. I want to talk about those a little bit tonight. The oceans are also changing in ways, and I really like the way this fellow Nicholas Gruber put it. They're warming up, turning sour, and losing breath. And so there is sea ice melt, there's increased stratification because the heating comes from the surface, and the ocean is much cooler down below, and if you warm the surface, then it becomes even more stratified. That cuts down on mixing. It cuts down on the mixing of oxygen further down, which is important for all living organisms within the ocean, whether they're phytoplankton or fish or whales or anything else. It also leads to global sea level rise, and there is acidification because of the increased. Some of the carbon dioxide goes into the ocean, and the ocean is becoming more acidic, and there is oxygen loss. A big part of this is from the nutrients from land, the pollution that goes into the ocean, and together that has consequences for phytoplankton, which is the beginning of the food web in the ocean, and dead zones are increasing. So here's the record of the global mean temperatures over the last 150 years or so. You can see lots of zigs and zags up and down. If we add carbon dioxide to this using the same base period, the base period here 0 means the average for 1900 to 1999, and I'll put these on a scale together to suggest that there's a relationship between them, because we think we can prove that there is. That requires climate models, computers, and there is this overall relationship, but there's still a lot of structure in the global mean temperatures which is not related to the overall changes in carbon dioxide. Carbon dioxide pre-industrial levels were about 280 parts per million by volume. Now they have just gone through 400 parts per million by volume. They haven't stayed there because in the spring there was a drawdown again, but they will go back up 400 parts per million by volume by later in the fall. Now, one of the foci of some of the deniers of climate change has been to suggest that there is a stalling of global warming in recent times. So what I've done here is to blow up the temperature curve for the last 40 years or so, from 1970 on, and it looks like this. You can see the listing of all of the warmest years. All of the warmest years are in the 2000s except for 1998. And the 2000s are the warmest decade by far on record, as far as we can tell, going back 2,000 years. If we put a straight line through this, it's actually not that bad a fit. There's some fluctuations up and down. Some of these fluctuations are related to the phenomenon known as El Nino. But what has happened in some of the rhetoric with the deniers of climate change is they've focused in on this little piece here and said, oh, look, there's a downward trend. If you take that period, in fact, the red dots on here, and put a straight line through that, of course you have to take into account all of the points. It is up, but it is not as steeply up as the overall warming since 1970. But of course this is also selecting the highest value, which was 1998, which was the big El Nino year. That's the time when the term El Nino came into the American vernacular, in fact the vernacular worldwide. It's been known by scientists for many years, but there was a huge outpouring of heat from the Pacific Ocean that made that year warmer than any other year up till that point. And by selecting that, you can distort this overall record. The overall record shows an upward trend, but at least in recent times, it hasn't warmed at quite the same rate, apparently. So has it happened before? Well, you can take that recent period and line it up here and say, well, it's not quite the same, but boy, you wouldn't expect it to be either. And these sorts of things actually happen. And they happen in climate models that we can run. So if there's more heat that's available because of this blanket that we've put on the planet, where does the heat go? Some of it warms the land and the atmosphere, including the surface. Some of it goes into melting sea ice, and it warms the melted water. And Arctic sea ice is at record low levels. I'll show you that shortly. Some of it goes into melting land ice. This is Greenland and all of the glaciers. It convects the Rockies and other glaciers out in the Sierra Nevadas and so on. And that water adds water to the ocean and therefore raises sea level. It goes into heating the ocean, and this is the main memory for the overall system, and that also raises sea level. And then it can also evaporate moisture, and I'm going to talk a bit about this shortly, and the effects on rainstorms and clouds, and the possibility then is that some of this heat gets reflected back to space. Over 90% of the heat, in fact, goes into the oceans. Of course, the oceans cover 70% of the Earth. You've probably seen pictures like this. There are many of them showing before and after the kind of retreat of glaciers in many parts of especially the northern hemisphere, showing the melting of land ice. And then the Arctic sea ice last year, 2012, was the record low. This year it doesn't look like it's going to be quite so low. It'll be somewhere in the lowest 4 or thereabouts, I think, this year. But, there's been a drop in the overall value of about 40% in summertime in Arctic sea ice. So this is a very clear indication that the planet is warming. And most of the heat goes into the ocean. And we've done a recent analysis of this, and we've published this particular curve here. The data in the ocean are pretty not too good up until about 1970. The errors are fairly large. The main warming that has occurred is since 1970, but you'll see it's not uniform, and you can also see a little bit of this leveling off in recent times. Well, this is the heat estimated for the top 300 meters of the ocean. We can then do that for the top 700 meters of the ocean, and it looks like this. And we can do it as best we can for the full ocean, and it looks like this. And so when you look at the full ocean, you'll see a slight leveling off toward the end here, but nowhere near as much. And so one of the things which has happened is, as you can see from here, a lot more heat is going into the deeper part of the ocean. And it turns out this is related to changes in winds, especially over the Pacific Ocean. And therefore, it's not being manifested as strongly at the surface. But the planet as a whole is certainly warming up. We can look at a few other things in this record. There was a sharp drop right in here, and right in here, and right here. And it turns out, right at this point, is when there was a major volcanic eruption that went off. This was Mount Agung, this was El Chichon, and this is Mount Pinatubo. And they were all in the northern tropics, and they caused a planetary-wide cooling, and that shows up very well in the ocean heat content. Also showing up here that I've highlighted is this big El Nino event, 1997-98 El Nino event. And it takes quite a lot of heat out of the ocean. There was actually a cooling in association with that had some effect for several years. And this is why 1998 is the warmest year on record. So heat can come in and go out of the ocean in various ways, and it affects the weather and the patterns of weather around the world. When we published this article, right out of the blue, this woman, Lynn Page, sent me a limerick. She said, "I like writing limericks, and here's my limerick related to your paper. There's a clearer analysis forming of the increase in powerful storming, but it's not just hot air about which we should care, for the cold ocean depths have been warming." I thought this was quite good, but I said, "Where's the title? You didn't send the title for this." And so she said, "I wasn't quite sure what to call it, and I'm not too sure about it, but this was the suggestion." I laughed. I thought this was absolutely hilarious, because with the warming planet the way it is, we are indeed in deep doo-doo. So I want to talk about one aspect of this which may not be so obvious. People associate higher temperatures with global warming, but I want to talk about another aspect of it relating to storms and rain and water. And so those of you who have been on hikes, if you go up in the mountains, you will know that if you haven't got a bottle of water with you, you can end up with heat stroke. And how does our body keep its temperature at 98.4, 98.6 degrees, so constant? The main way is through perspiration, through sweating, and that means you've got to have a water supply in order to enable that to happen. Out here in the West, we can use evaporative coolers called swamp coolers, and we moisten the atmosphere, but at the expense of, but then we can keep it cooler. And for planet Earth, this works very well, because 70% of the planet is ocean, and so the heat goes into, instead of warming up the ocean, it goes into evaporating water, and that, of course, gets into the atmosphere, and, of course, it is a key part of the water cycle, the hydrological cycle, and gives rise to all the rain and the rivers and everything else that goes on. Another example, what happens if the sun comes up after showers? The first thing that happens is that the puddles dry up. And then the temperature tends to increase. And so water is the air conditioner of the planet. It's very important. And so if there's extra heat, some of it goes into changing the water cycle. So how should rainfall, precipitation change as the climate changes? And often people only really talk about the total amount. And yet the things which change probably more are some of the other characteristics of precipitation. After all, precipitation is intermittent. There was a few little spritzes out there today, but most of the time it doesn't rain, right? And in fact, on average, we estimate on a global basis about 7% of the planet is raining. It depends a little bit on your threshold as to what that number is. But so that we need to pay attention to the frequency of rain, the duration of rain, the intensity of rain, how hard it rains, when it rains, and the sequences, because this determines whether there is drought or floods, for instance, and also the phase, whether it's rain or snow. The intensity and the phase affect how much runs off versus how much soaks into the soils, as an example. And so, in a case of two hypothetical stations, Station A and Station B, this is 1 month's worth of data. The two stations got exactly the same amount of precipitation, but it was distributed very differently. In Station A, the frequency is 6.7%, and the intensity when it rains was 37.5 millimeters. Remember, 25 millimeters is about an inch. And it's a factor of 10 different for both quantities in the case of Station B. And so, what's the climate like in these two places? In Station A, it's a dry period. There may even be drought, wilting plants, and an increased risk of wildfires. And then suddenly, there's enough rain here that it will cause gutters to overflow, culverts to overflow, some local flooding, underpasses and highways to fill up. On this case here, the soil moisture is replenished from the evaporation that occurs every day. This is probably great for plants, very good for agriculture, but none of it ever runs off. The streams dry up, the rivers dry up. We actually have a hydrological drought in this case. These are very different climates if you had this kind of distribution of rain. And yet what is happening is that we're going more from a climate that's like this to one that's a bit more like that. Longer dry spells, more intense rains, but the total amount, it's up and down. So why does it rain? Let's understand some of this a little bit more. Here's a nice picture of a rainstorm in the distance over the ocean. One of the key factors, maybe if you want to learn a new number, you might remember this one here. Warmer air holds moisture at a rate of 4% per degree Fahrenheit of warming. It's actually an exponential function, which is why we express it this way as a percentage. 4% per degree Fahrenheit. And so in the actual atmosphere, if it's warmer, we find that there's more moisture in the atmosphere as long as moisture is available. And of course, this is always true over the oceans. It's true certainly in coastal regions. In deserts, there's no moisture available. It doesn't matter how hot it's got, there's no extra moisture. What this says is that the atmosphere actually tries to keep the relative humidity about the same. So let's take a parcel of air. I've put a line around a blob of air. And what happens if this parcel of air rises? And it can rise for all sorts of reasons, whether it's a part of a storm, and the air gets forced up as a part of a storm, or part of a warm front or a cold front, or through heating, which causes it to rise through convection, or it runs into a mountain and it gets forced up by the flow of air over a mountain. There's lots of reasons for air rising, but when it rises, it moves into a thinner part of the atmosphere, so it expands. When it expands, it cools. And that's why it's cooler, of course, when you go up in the mountains, when it's because the air is thinner, and the air, when it rises, automatically cools. And so it can no longer hold moisture, and therefore the moisture condenses, it forms a cloud, and then it rains. This is very fundamental as to why it rains. So having the fact that the amount of moisture that the air can hold be a function of temperature is the main reason we have the water cycle and rain the way it is. So here's this thing going up, and then, wait for it. Oh, there it is. And lots of rain. All right. So, and so we have this number, and then with global warming, there's more heat, so there's more drying. There's always that tendency. That means there's more evaporation as long as there's moisture available, and that puts more moisture into the atmosphere. And so in places where it's not raining, we end up with droughts, more stronger droughts. And the places where it's raining, it actually rains harder because there's more moisture in the atmosphere. And the way in which that works is through a big storm, and this occurs with all kinds of storms, whether it's a hurricane, a thunderstorm, or a big extratropical snowstorm. All of these storms reach out through the circulation of the storm, through the winds in the storm, and they suck that moisture into the storm from remote areas. And of course, this is why it can't rain everywhere all at once. If it did, it would be a very, very light rain, because the average evaporation rate on a global basis is only about 3 millimeters per day. 3 millimeters per day. So how can you possibly get 30 millimeters per day, 1 inch of rain or anything like that? And of course, most of the time it rains a lot more than that. And so the moisture comes in, gets sucked into the storm, and as a result, if there's more moisture in the environment, it rains harder. And that's what's happening in the world today. Another factor related to the type, the snowpack. More precipitation falls as rain rather than snow because the air is a little warmer. This is especially true at the beginning and the end of the snow season. The snow melt occurs faster and sooner in the spring, and therefore the snowpack tends to be less. This is very important in many areas. It's been a very big factor in the wildfire season in the West because there's less moisture and the drying then occurs, especially throughout the summertime. And so as a result, the risk of drought increases in summertime along with the risk of fire. This was actually a fire, the Hayman wildfire here in the Denver area in 2002. And so we have these changes in extremes. With a warming climate, we expect more high temperatures and heat waves. Wildfires and other consequences go along with that, fewer cold extremes. But we also expect these additional extremes in the hydrological cycle, in the water cycle, more intense precipitation and longer dry spells, which increases the risk of flooding and drought. Now, I say it increases the risk rather than saying increasing these things, because we can mitigate these things by irrigation in the case of drought, or by having good drainage systems, right? Doesn't have to result in a flood, but that's the tendency. And there are more intense storms, hurricanes, and very likely tornadoes, as it turns out. And so this provides major challenges for a water manager, because instead of the nice gentle flows that we had to deal with before, we either get nothing or we get gushes of water, more so. And the basic factor here is that the environment in which all of the weather occurs now, all of the storms occur, is simply different because of human activities. This is my slide to introduce the fact that at NCAR we do a lot of climate modeling, and these are the processes we try to put into a climate model. All of the interactions between the atmosphere and the ocean and the land surface, and we have to represent it in discrete fashions using levels. And we do a reasonably good job at this. We certainly are getting better at this. And this is some results of a model run. This is actually 6 runs that are averaged together, so it cuts out most of the weather, showing the values, the annual values. You can see the clock ticking there from 1930, now 1940, 1950, over time. And you'll see that the biggest warming occurs on land, and especially in the Arctic. There's a bit more down here in the Antarctic. There's one little spot there in the North Atlantic which hasn't warmed. That actually relates to changes in the Gulf Stream. The Gulf Stream has come further south as a consequence of this. And so that little spot has not warmed. And so the warming is not uniform. And this has consequences for ecosystems. So, as a brief summary, global warming effects from humans are already identifiable in a number of different ways. And I've written on the right-hand side in white some of the consequences associated with that. And I thought what I would do in the last part of this talk was to talk about some of the extremes that have occurred, which we think are influenced by climate change since 2010. And so in 2010, 2011, there was a lot of major headlines associated with the Russian heat wave and all the wildfires, and 75,000 lives were, or greater than 50,000 lives I've got here lost. I may not have remembered that correctly. Not very far from Moscow. So this you may remember. This is St. Basil near Red Square as an iconic picture of the wildfires that occurred at that time. At the same time, there was flooding in Pakistan and India, in another part of the Eurasia. A bit later in the year, there was some major flooding in Queensland that had headlines. And so this is the area in Australia that was especially affected at that time. This was December 2010 into January of 2011. But in actual fact, it was very wet in Australia from August 2010 till April 2011. And there are many places on here which was the wettest on record. And a colleague of mine has just published a paper dealing with this particular event. And Australia is unique among all of the continents because it's in the subtropics, it has a big desert in the middle of it, it doesn't have a riverine system, and so you dump a whole lot of water in the middle of this continent, it sits there. And a big new lake forms, it's called Lake Eyre, right in the middle of the continent, and it takes a year, 18 months to dry up. Whereas most other continents, the water runs off and may get back into the ocean within a couple of months. So this had a consequence for sea level. This is the sea level record since we've been making measurements from space using altimeters on satellites looking down at the surface of the ocean. Prior to that, we just had measurements in coastal regions and islands. And so the overall rate here is 3.1 millimeters per year. The overall rise in this, that's the straight line on here. You can see some fluctuations up and down. Some of those are related to El Niños to some extent. And then there's this remarkable event right in here where things dropped abruptly by about 6 or 7 millimeters below the straight line expected. And in fact, this was Australia filling up with water more than anything. At least 3 millimeters of the global ocean was dumped into Australia and taken out of the global ocean. And there were some other places that contributed a little bit, including some other parts of the world. So this was at a time, if you can think back a couple of years, remember all of the flooding in the Missouri and in the northern plains, and this was associated with snow. And of course that takes water out of the ocean, dumps it on land, and it sits there for a while until it melts. So that's the other way in which you can save water on land. There was tremendous flooding in Venezuela and Colombia, but there are rivers that carry that back into the ocean on a relatively quick basis. This certainly is associated with snow, and also in South Africa. And so all of this extra water on land led to this dip in the global sea level, but sea level was going up. This is perhaps the best indicator of global warming, even better than the global mean temperature, because this is a combination of the expansion of the ocean and the melting of land ice filling up the ocean with more water. I think I'm going to skip through this very quickly. This is what was happening at the time in 2010. There was record high sea temperatures in both the Indian and the Atlantic Ocean at this time, And so this is what this says in May, and in August there was record high temperatures. There was record high temperatures off the coast of South America in September, and also just north of Australia in December. So it turns out the flooding that was occurring in Pakistan and India, the active hurricane season, all of the flooding in Colombia and Venezuela, and the flooding in Queensland was very much associated with these record high sea temperatures in adjacent oceans. And so the winds, the monsoon winds in particular, are picking up more moisture and carrying it onto land and dumping it down in the form of heavy rains. What about the U.S.? So a few slides about the U.S. This is 2011. 2011 was remarkable. You may remember, think back, Texas was the driest and the hottest on record in 2011, but not too far away up here in the Northeast, it was the wettest on record. I mean, this was very remarkable. We had all of these storms barreling across the United States. This was the year which we had all the tornadoes, you may remember. And yet, part of the country was exceedingly dry, and other parts of the country were extremely wet. In other words, the storm tracks were locked in place. And they were locked in place by a phenomenon called La Nina, the cold conditions out in the tropical Pacific. And so here's an example. This is sort of before and after in 2011 for the Mississippi, the river, and tornadoes galore. That was the time when we had the Joplin tornado. And Arizona was on fire at that time, some of the biggest fires on record. And Texas had over 60 days, 65 days in Dallas with days over 100 together. And June, July, August, the hottest on record. Some went more than 60 straight days over 100. And there was the biggest fire on record in Texas at that time. In 2012, we got it everywhere. Nearly, not everywhere. We have it nearly everywhere in the United States, except for the Pacific Northwest. And there were 362 all-time records in 2012. There were 3,527 monthly weather records. There were 0 record low temperatures that occurred. Ooh. And so in June, this is just over a year ago, remember, this is June, in this area, not too far from here, there was the Waldo Canyon fire near Colorado Springs. 346 homes were burned. The High Park fire up near Fort Collins, 259 houses were burned. And this is the picture just to the north of here, 30 miles to the north of here, in Boulder. And that's the institution where I actually work. This is NCAR. Feel free to come by and have a look. And there was a fire about less than a mile away from us that shut us down for a couple of days because the air quality was so bad. And then, of course, we had Superstorm Sandy. Superstorm Sandy, we estimate, was about 5 to 10% stronger as a result of global warming. And in addition, it was riding on top of, overall, 8 inches of extra sea level because of global warming. In the New York City area, sea level is about a foot higher than it was in the early, in the 1800s, thereabouts. And there was over $70 billion in damage. And I reckon that more than half of this is due to global warming. Let me say that again. More than half of this, probably $40 billion or something like that, is due to global warming. And the reason is because you crossed certain thresholds. You cross a threshold in the Manhattan region, and what happens is the subway system fills up with water. The tunnels fill up with water between Manhattan and Hoboken and New Jersey and with Brooklyn. None of those tunnels would have filled up if the sea level hadn't been higher and the storm hadn't been as strong. And that's sort of what is happening with the previous year in 2012. Whoa, gone backwards. here, where we had major drought. The estimate cost of this is somewhere in the same ballpark, somewhere around $75 billion. And again, it's all very well to have hot, but when you're breaking records like this, you're going outside of the bounds of previous experience. That's caused by global warming. And as a result, the damage, the wildfire risk goes up, and the damage goes up, and the crop loss has a big factor, which is very hard to estimate. It's very hard to prove these kind of numbers. What about 2013? 2013 started with Australia having record high temperatures, in Sydney, 115 degrees Fahrenheit. Tremendous wildfires. There were April showers, quote unquote, lots of flooding in Argentina. This is the U.S. This is what the drought picture actually looked like at this time in June. It hasn't changed a huge amount. Very dry throughout the West. And we had the big dust storm in Colorado and a major wildfire, the Black Forest Fire, where there was over 511 homes burned, again, down near Colorado Springs. And then this is going on right now. This is the so-called rim fire. This is a picture of it from space, from NASA. And this is a picture of it from the ground. So this is reported to be one of the biggest, what is it, the top 3 or 4 biggest wildfires in California at the moment. And you can look at the western U.S. and look at the changes in wildfires and wildfire statistics. This is actually taken from a website where you can actually go in and look at all of these in a lot more detail and pick on them. But, wildfires are increasing in association with the warming and the drying. Other parts of the world is flooding in Germany. This was the Elbe River in May of this year. And how many of you remember these tremendous flooding that occurred in Alberta, Canada, in Calgary in June of this year? Absolutely devastating in that region. And so this is the Northern Rockies, tremendous rainfalls up in there, up to over 300 millimeters of rain, 10 inches plus of rain in the Northern Rockies that caused that flooding. And in India they also had some tremendous flooding this year. And then where was the hot spot? It wasn't in the U.S. this year. We've had certainly some heat waves, but they were short-lived. In general, it's been wet. There's been some record flooding in the southeast in particular. This is where some of the hot spots were in China and further to the west in China. This is actually Shanghai, showing some of the very high temperatures over 90 degrees. And so they actually got up to 105 degrees in Shanghai. And this is pretty remarkable considering the pollution that's there that's blocking the sun. So I'm going to close this. This is just my view on things, given all of the evidence, is that as we've seen, I think there are major costs, billions of dollars, associated with the droughts being stronger, more intense, the increased risk of wildfires, and the flooding that has occurred around the world. There's big impacts of those. This year, what did they say? We're already way overspent our budget simply in fighting wildfires without accounting for over $1 billion in firefighting costs, let alone the losses associated with it. And the costs are not borne by those who cause the problem. There's no direct user pays concept associated with the use of fossil fuels. And so there are a lot of explicit, and there's a lot more even implicit subsidies for fossil fuels that do not make the playing field level for renewable energy. The implicit ones are all of these things relating to what we might call security for the Middle East. Maybe the whole war in Iraq could be put in that category. And the U.S. is a major part of the problem. And so this is, President Obama is trying, but the real problem is in the Congress, and the U.S. is not leading in the international arena, and nothing much is happening. And just remember, folks, there is no planet B. Thanks.
Questions? Comments? Kevin?
Yeah.
Kevin, the other Kevin.
Yes, I have a small question and a comment that probably is a question too. The small one is that when I first started hearing about global warming quite a few years ago, the emphasis was on CFCs. And now the emphasis is on carbon dioxide. And I wonder what's the explanation for that?
Well, CFCs are certainly a greenhouse gas. They're a very powerful greenhouse gas. But the emphasis on CFCs came because of the ozone hole more than anything. And so there was the Montreal Protocol and a series of follow-on protocols that occurred. And so as a result, CFCs have been phased out of aerosol cans and air conditioners and things like that, mainly because of the effects of CFCs on ozone and the depletion of ozone and the ozone hole in the southern hemisphere. And so that has a direct relationship to the increased risk of cancer. And so I think that's why CFCs were so much in the news at that time. It was only incidental that CFCs were also a very powerful greenhouse gas, but the concentrations are so much smaller that they are only a very tiny part of the overall greenhouse effect.
That makes sense. Now, I have this other question, which is that although there's been a great deal of discussion of global warming recently, and a great deal of emphasis on the contribution of human industrial activity, there has been very little in the way of discussion of the driving factor, which, of course, is human population growth.
Yes.
And until we take that seriously, it just seems to me that that's a losing game, that the human race has to sooner or later get it, that the resources of the planet are finite, and that we have to rein ourselves in before nature does it for us and we kill off a good portion of the human species. And then also, there's a lot of controversy about global warming, but the thing that's left out of the debate usually is that, okay, let's suppose that we don't know. Whether global warming is going to continue and how bad the climate change is going to be. But just assuming we don't know, the prudent thing for the human species to do would be to put on the brakes on both population and industrialization right now. And I just don't hear the voices calling for that I would like to hear.
The larger issue is certainly the one dealing with sustainability of many things. We're going to run out of certain kinds of things because we're using them at a rate, and many of these things are not renewable, and we don't recycle them adequately, and so on. I think one of the biggest pressure points with regard to climate change is actually water, and so that's part of what my talk was very much about. Rather than temperature, we can always crank up the air conditioning, right? But that's putting more carbon dioxide into the atmosphere. The whole thing on population is one which is invisible, and the U.S. has been very much responsible for that, the lack of any emphasis on population. And this comes because of some of the funding constraints that have come, especially out of the Republican Congress. And yet, if you go into a debating chamber with the Chinese and the Indians, who have huge populations, China is now emitting quite a bit more per year than the U.S. But they will say they're emitting a factor of 4 times or 5 times less per capita than the U.S. The atmosphere doesn't care about per capita, but the arguments that occur about who is responsible for doing something about this often bring in that per capita aspect. And of course, this is a big issue with India. It's even more an issue for, if you want to think about it this way, waiting in the wings. Africa, what happens when Africa comes along? If it's fine, if people if we want to have a large population existing on $1 a day, but if everybody wants to have a refrigerator, a reasonable standard of living, something approaching even a good fraction of what we have in the United States, then the population, the planet is already overpopulated. And it's said that, well, as further development occurs, the population will level off. And so the predictions are that, we're at 7 billion now. It'll level off at somewhere around 9 or 10 billion, maybe. But can we really sustain that? I very much doubt it. And of course, what happens? The classic way that this happens. This is classic boom and bust stuff, right? This is a boom. There's a boom. Things are no longer sustainable. Suddenly, all kinds of things happen, and there are various kinds of scenarios as to how that can happen. Some of it is certainly through strife and conflicts and increased conflicts. A lot of it is through environmental refugees. What happens if you no longer have sufficient water to exist? For instance, you have to go somewhere else. You're crossing borders. You can't come here. This is our water. This happens even in the U.S. The only thing is, in the U.S., there are tens of thousands of lawyers, and all of the wars that go on are actually in the courts over water rights. But water is a big issue, and there's been some outbreaks even between states when it's been dry in the southeast. Tennessee and Georgia and so on are having at it. Louisiana and so on are having at it because they haven't got enough water. So yes, this is very much a part of that bigger issue. This has stimulated a few more things, but yeah.
Yes, I know you're not really an oceanographer, but I do understand that there is a direct relationship between the Gulf Stream and its purpose and
you have to speak into that so it gets recorded.
Right. Oh, okay. Yes, I understand that there is a direct correlation, some relationship between the health of the Gulf Stream and the climate change, and the effects that increased temperatures worldwide may have on that Gulf Stream. I mean, we tend to think of it, it's down there deep in the ocean, it won't change, but I understand that it will.
Well,
that will have a devastating effect.
As you could see in that model portrayal of the temperatures going into the future, the North Atlantic had some peculiarity in that there was one spot that didn't warm. This was taken in science fiction, let me emphasize the fiction, in a movie called The Day After Tomorrow. They said, it's going to cool in the North Atlantic. Next thing we know, we're going to have a big ice age, and here's this big drama that comes out of that. Well, it was based upon this idea that indeed the Gulf Stream could shift and it could change things. But there are indeed, because of changes in ocean currents, and it's also very potentially could happen in the southern hemisphere, where the similar kind of dynamics and effects occur, that there are some spots that may not warm up because of changes in the currents. But it will certainly affect fish and all of the marine organisms. But it's a part of the bigger picture.
And how we're going to feed that huge population.
Karen?
Okay, I've got this now.
Whoever's got the microphone gets to speak.
Right, okay. What do you see at this point in time and then into the near and further future as being the most significant and potentially promising movements or projects or what have you to address the problems on, say, a national basis and, more importantly, a worldwide cooperative basis where we're looking at working with China, India, everybody as a planet? Because obviously it's a problem. I think people are beginning to accept this if they have not necessarily previously, but we need to look at the future. So while we have all this information, I guess my interest is in what is being done and what can be done in the future, and are we having really any success in cooperative ventures on a wider worldwide basis?
Yeah, and so there's a lot of things individuals can do, and you've probably been encouraged to do that. I have solar panels on the roof of my house, extra insulation in the attic, driving a small car or driving less, riding a bicycle, good exercise, and cutting down your personal carbon footprint. But the overall framework for this really doesn't exist nationally and especially internationally. And so, California tries to do certain things, and a company says, if you impose any kind of a penalty, a fee, or a carbon tax, I'm going to move my company to the next state, right? This is happening in various places in the U.S. It's happening internationally. New Zealand, Australia had a carbon tax. It's sort of disappeared at the moment because they're just about going through an election, and it's a part of the election process, and we'll have to see what happens. But again, companies in Australia have threatened to leave and go elsewhere. And so not having this international framework is the major block to really moving this whole thing ahead. And I think in order to get that, it requires U.S. leadership. Europe has had cap-and-trade systems in place and has been leading the way with regard to reducing emissions in association with the Kyoto Protocol. The U.S. was the only country that didn't, or major country that didn't sign the Kyoto Protocol. And I don't think the general UN framework, which is the main thing that's been used, is the way forward. This is 180 countries potentially all saying their things, and many of them with their hands out saying, we're being affected by climate change, we want to get compensated for this, and they can make a case for that, but there's no pool. We haven't created a pool. This is where a carbon tax could also play some kind of a role. And so it requires the countries that are most responsible for this to get together. And I think the main framework for this is probably the G20. But the president, the U.S., has to be able to go in there and step up and play a leadership role. In the meantime, I think everyone's sitting back on their heels and not much is happening. I don't see it happening without U.S. leadership.
Yeah, I see that as being really critical and kind of a United Nations of let's save our ass before it's too late, educating people throughout the world. Really, like you're saying, nothing's being done that's significant in bringing about the change that we want to see, and I'd like to see something done.
Yeah, so certain things are happening now through the EPA process, with protests in Congress, but we'll see how far Obama can actually go. You've got the microphone.
On tipping points and knock-on effects, one of the more worrisome ones, of course, is the Arctic carbon. On the last IPCC report, there is no Arctic carbon in the models. And do you know if there's going to be Arctic carbon in the models this time, and how far behind the actual release would you guess they might be?
There are models that do the carbon cycle much more comprehensively and interactively. They're, I would say, not quite there yet in terms of being able to let them run fully coupled, fully interactively, because certain things don't quite work right, and there are differences among different groups. And so if you deal with carbon, you start trying to put carbon into a climate model, for instance, it's very easy to put carbon in by itself. But then it turns out, carbon grows in trees. Trees require nutrients. Nutrients come from rain. It depends on the water cycle, but it also depends on things like ammonia, if you like to think of it that way, fertilizer. And so then you have to put in the nitrogen cycle. Then you have to put in the phosphorus cycle. Then you have to put in all of these other trace species and how they cycle through the overall environment. And it turns out if you put in only a subset of processes, you can get one result. And there's been one that was published and got a certain amount of attention where, the Amazon forest disappeared. But it was incomplete. They didn't have all of the processes in there, and in other models, it doesn't disappear, right? And so there will be a lot more information. And certain, one of the other things is that there's melting or thawing permafrost. That frees up a lot of extra carbon, which is locked up in soils. And once that is thawed, there are two kinds of processes that tend to occur. There's microbial activity that occurs. If it's in a wet environment, it's like a marsh, and it forms marsh gas, methane. If it's if it dries out, if the bogs dry out, then it's more like what a healthy compost heap does, and the decay occurs much faster, and it forms carbon dioxide directly. The methane ultimately gets oxidized into carbon dioxide, but both methane and carbon dioxide are greenhouse gases. And so these kind of processes are the things that put more carbon into the atmosphere and amplify some of the changes that are already going on. And so that's the source of the concern in the Arctic in particular as to how things can get amplified. On the other side, and this is another part which is not quite fully assessed adequately, is that as things warm, then there are plants that can grow more readily in higher latitudes. Things can actually migrate and grow. And so there's a bit of extra green, which then takes some of the carbon dioxide back out of the atmosphere and puts it into vegetation of some sort or the other. There's a lot of discussion about offset schemes of different kinds. And should we grow trees? Let's grow trees. We'll take carbon dioxide out of the atmosphere. Carbon dioxide is a great way. Trees are a great way to take carbon dioxide out of the atmosphere. But it only works if you grow these trees, and the trees grow rapidly. Then you cut the trees, and then you grow more trees, and then you grow more trees. And what do you do with the old trees? If you use them for paper, if you use them for something, sooner or later they get back into the system. And so it doesn't take the carbon out of the system. The only way it really gets taken out of the system, you can think of the old churches in Europe or in England, where there are some churches that are 1,000 years old and they've got these big wooden beams. That wood has been taken out of the system for 1,000 years, but most of it doesn't get taken. So growing trees is great as a renewable energy source. It's a biofuel in that sense. But a mature old-growth forest actually creates carbon dioxide at the same rate that it takes it up. By definition, that's what a mature forest is. The rate of decay of all of the stuff on the forest floor, the leaves and the broken trees and things like that, is exactly the same as the amount that's taken up by the canopy and put into the wood in the first place. And so be very careful about some of these offset schemes as to how they work.
That partially answered my question. But
Gary, keep it short, please.
That's right. The biosphere naturally only takes out about 1 to 2 parts per million of carbon dioxide per century, and puts it, eventually washes it into the ocean where it gets buried. What I'm really concerned about is the carbon coming out of the ground from the methane, from the clathrates, the hydrates, the pools of carbon that are trapped underneath those frozen hydrates as they melt. Is any of that really large store of carbon going to be in the models? It's already coming out. It's bubbling. It's keeping the lakes unfrozen. It's bubbling so hard now.
The underwater landslide of thousands of years ago and all that.
That part is not in the models at this time. It's very, very hard to predict. The oceans are quite cold at the bottom of the oceans, and so the clathrates that are on the bottom of the ocean are probably stable for the most part. There are certainly places where some of these are being released, and the Japanese are beginning to harvest some of the clathrate nodules and things like that a little bit. I don't know how big that is. It's a part of the overall feedbacks that certainly doesn't help. Let me put it that way.
2 more questions. Robert?
I'd like to suggest that the emphasis on renewable energy and carbon credits is misdirected, and that there may be a technology that is carbon neutral, safe, and abundant that has not been adequately investigated, and we should be developing it, doing the science that remains to be done, and if it is feasible, implementing it as fast as possible. And that's liquid fluoride thorium salt reactors. There's great interest in this. The claim is that it is essentially, the nuclear cycle is essentially 100% efficient, that you are deriving essentially all the nuclear energy, potential energy out of the fuel, breaking down long-lived radionuclides into things that only last a few dozen years, and that it's intrinsically safe design, et cetera, et cetera, et cetera. It's 4 times as abundant, according to some people.
I don't know anything really about that. The key thing on all of these technologies is firstly the cost, and then secondly how energy intensive they are themselves. Often it takes energy to make energy. This is again the sort of thing with regard to all of the mining of the tar sands up in Canada at the moment, and this Keystone pipeline which has been proposed. The net gain is not that great. If there were a tax on carbon, it would make the economics of that just completely different altogether. And it would make the economics of many of these other things different as well. Nuclear, potentially could be part of the solution in various ways, but for the most part, since Fukushima in Japan, it seems to have priced itself out of the market.
This is Jeff. I was just wondering, do you think we're approaching a point of no return where it doesn't matter what changes we make, that we aren't going to be able to avert any kind of a disaster because of global warming?
We can avert disasters, but we're going to experience climate change. We're going to continue to experience climate change. But the rates of change matter enormously. If we can slow them down enough, then we can experience them as we go along, and so we can adapt to them, what you might call autonomously. This is especially in issues relating to farming. How do you plan a farm, and the use of fertilizer and water, and what seed and what crop you're going to, not only what crop, but what type of seed, and is it drought resistant, various other kinds of things. All these decisions have to be made. And, as the climate changes, if it's gradual enough, you can perhaps sort of go with the flow and adapt to some of these things. But if it happens too fast, suddenly you're trying to grow something which no longer grows there anymore. Maybe it grows somewhere else, but maybe it doesn't grow somewhere else, because it's often said that we can just move things further north. But further north, the light is not the same as where it was. And so the lighting conditions are different. The soils may not be the same. You can't just move things around like that. Certainly it's the natural ecosystems which are apt to suffer the most. Many of our trees, they're talking at the moment about the risk to the big trees out in California, and you burn those down, maybe they will never grow again in that region because they're no longer viable there. And many of the trees in the U.S. have a natural lifetime, say of order 100 years or something like that, and so causing rates of change where they have to regenerate, and a new version regenerates every 30 years, is simply incompatible. And there's a lot of dislocations of different kinds that are occurring in nature already through different cycles, bugs happening, hatching sooner, whereas the birds that normally feed on those bugs are still hatching a bit later, and when the birds come out, there's no bugs for them. And then we get a plethora of bugs, and we lose all the birds. And these kind of mismatches are occurring more and more in nature as well. And so it's the rates of change, I think, which is the biggest concern. And we're going to have to live with a certain amount of climate change, but we can also slow it down to a point where we, in principle, could manage it. In other words, this is the adaptation aspects. We need a combination of adaptation and mitigation in order to address this problem. And we're not doing enough of either at the moment.
I have a couple of technical questions relating to the methodology that I'd like to ask. They're both quick ones. First of all, I have a very good friend who's a historian, and most historians would consider the Industrial Revolution to have begun in the late 18th century, around 1770. But all of the charts that I have seen relating to temperature and so forth began in 1850 or thereabouts, including the one you showed at the beginning of this lecture. What is the reason for choosing that date as opposed to what is more or less the consensus for the beginning of the Industrial Revolution?
Well, in terms of the record of climate, we try to push the values back as far as we possibly can, and 1850 is about as far back as you can go with the instrumental record. That's when there's been enough. You can argue actually whether there really was enough observations to put forward at least a northern hemisphere view as to what the temperatures were and how they're changing. So this is when ships started carrying thermometers and making some measurements and things like that. Going back further, there are individual places, individual locations in central England. There's a record that goes back into the early 1600s, temperature instrumental record. But before that, we have to use so-called proxy records, and this means indicators of things that are sensitive to temperature and precipitation, things like trees, tree rings, ice cores, corals, even sediments that are in lakes and other places. Paleoclimate continues to devise devious and brilliant ways to get information about what the climate looked like at various places in the distant past. But that's the restrictions are, measurements that weren't made are lost forever.
Okay. The other question relates to the modeling that's being done. As an engineer, I've done quite a few computer models, and I'm quite familiar with the idea that the devil is in the assumptions that you make going into a model. Do you or does anyone publish with these models and make available the assumptions that go into these models? Yeah. And if so, where can they be found?
Yes, and so there have been major projects. At the moment, the one that's used in the latest IPCC assessment is called CMIP-5. In the 2007 assessment, it was called CMIP-3. What is it? Climate Modeling Intercomparison Project, I think is what CMIP stands for. And so there are some 25 or 27 different modeling groups or different models around the world. Actually, some of them are from the same modeling group, but the different versions of the models that have been used to produce scenarios going into the future, and also simulations as to what has happened in the past. And all of these groups are responsible for writing up their results and documenting them. One of the strengths of, actually it's done through the World Climate Research Program, which I've been very much involved with, in order to make these projects actually happen, is this intercomparison projects that does give you 20 different flavors of the different assumptions that are made in different parts of these models, and understanding why one model differs from another. It turns out it's not a trivial task at all, and rather small things that you wouldn't think might matter very much through various nonlinearities can very easily become important in some fashion. I sort of referred to some of these a little bit with regard to the carbon cycle and some of the complexities, and that it's very easy to put 3 or 4 of the dominant processes that are important with regard to carbon in there, but if you haven't got the other ones in there, then some of the feedbacks, the negative feedbacks or the positive feedbacks, are not included, and different modeling groups make different decisions on this. So one of the more robust ways of dealing with those kind of things is by having these different groups that are indeed free to make different assumptions rather than putting all of your eggs in one basket, all of the resources into a single model that that maybe we can run more completely and with more complexity, with higher resolutions, much longer, and things like that. That's one of the kind of arguments that goes on within the community. But the diversity of the models is actually one of the strengths of the system as well.
That's very good, but where can I find these?
Oh, well, they're available. If you wanted to Google CMIP, you can find websites where a lot of the basic information is. But most of the individual, it's probably not all together in terms of the details. A lot of it is in the IPCC report. So the IPCC report that's coming out in September will have a modeling chapter which does intercomparisons and which describes a lot of these things and the differences in the decisions that are made. And you can find that in past IPCC reports as well. But the real details are in individual research papers that have been published in different journals. So they're all over the place.
I think the questions will never end. Dr. Trenberth wanted to be out of here about 8:15. And so it's 5 minutes past. So I'm sorry, not everybody can get in on this battle over climate change. But thank you very much, Dr. Trenberth, for coming back in.
Yeah, I'm going to Rio tomorrow. I'm chairman of a group under the World Climate Research Program, basically under the United Nations, and there are two of the panels under my group that are meeting in Rio de Janeiro next week. So they'll be meeting individually a little bit and then jointly, and then we're having a 2-day workshop with South Americans on water. And so that's what I'm doing next week.
Save the planet for us, please. Thank you very much. I think we're done for tonight.